Okay, so let's take a look at this sample problem. So it says a parallel plate capacitor with circular plate of radius r is being charged. Derive an expression for the B field at radius r for the case r is more than capital R. Okay, so here we have this circular capacitor 有一个圆形的电容要叫我们推导这个 B field 因为现在有一个电流一直流进去所以这个 E field 也会一直在增加。Okay, so so according to the Maxwell's law, we can write integration of a B dot ds equals mu 0 epsilon naught d phi e dt. Okay, so this is nothing but the Maxwell's law itself, and then we can go through several steps. Integration of B times ds equals mu naught epsilon naught and then d and then ea dt. Okay, so on the left side we will take several steps. Okay, so for the first step B dot ds equals B times ds because they are parallel to each other and have the same direction. Okay, so we go to here, and then for the next step we can put it outside, so it becomes an integration of ds for a circle. So it is nothing but 2 pi r. Okay, so this is what we have done previously for the Ampere's law. Okay, so this is also the same case for the Maxwell's law here. Okay, because we assume all the situations are symmetrical. Okay, so this is a circular capacitor, and then we also consider an Ampere's law which is concentric to the capacitor and then smaller than it. So we will expect the B field is like have the uniform magnitude, although the direction are changing. Okay, it is like a circle, like the tangent direction of the circle. Okay, so on the right side here, phi e equals ea. Okay, we just assume the E field is uniform inside the capacitor. Okay, so this is just our assumption for the capacitor. So this surface integration turns out to be a multiplication, and then A is a constant, so we can put A's out. So we have a mu 0 epsilon naught and then A dE dt. Okay, and then on the left side it's the same, and then on the right side mu 0 epsilon naught, and then this is the area of a circle, so this is a pi r square, and then dE dt. So now the r is smaller than capital R, so the area is considered to be small r. So finally B equals mu 0 epsilon naught r over 2, okay, and then times dE dt, something like this. Okay, so this is the expression for the B field with r is smaller than or equal to capital R. And then for the second case, okay, so here we try to evaluate the field magnitude B for r equals capital R over 5 and d equals this value. We just plug in the number there. So B equals mu 0 epsilon naught r over 2 and then times dE dt. So mu 0 is 4 pi times 10 to the negative 7 times 8.85 times 10 to the negative 12. And then r is here 11 times 10 to the negative third power over 2. And then dE dt is this one times 1.5 times 10 to the 12th power. Okay, so this is nothing but 9.18 times 10 to the negative 8 Tesla. Okay, so this is the induced B field given these values. Okay, so for the next one, we try to calculate the B field when R is larger than capital R. So which is so here the Ampere loop is bigger than the capacitor. Ampere loop here. Okay, so in that case, integration of a b dot ds equals mu naught epsilon naught d phi e dt. Okay, so in that case, on the left side we have a b times 2 pi r, and then on the right side we have mu 0 epsilon naught a times d dt, just as before. Okay, I don't repeat it again. Okay, but here the difference is that this a, okay, consider this is the Ampere loop, but this A related to the electric flux. Okay, so the only part generate the electric flux is only the inside part. Is only the inside part. So this part don't generate any, don't contribute to the electric flux. So in that case, we should use pi capital R square instead of pi small r square. So dE dt. So in that case, B should be mu naught epsilon naught capital R square over 2 small r, and then times dE dt. Okay, so this is the expression. This is the expression for the B field that is outside the capacitor. Okay, so yeah, so this is it. We don't have any number to put in it. Okay. Yeah, so far, if there's no question, we move on. So here, as I mentioned, okay, we have something called the displacement current. 中文叫做位移电流。位移电流，位移你们知道，电流也知道，但是它们放在一起的话，就是你不知道它在做什么。So in that case, okay, if you compare the two terms on the right side of equation Ampere-Maxwell's law, you will see that the product, this one, okay, must have a dimension of a current. In fact, that product has been treated as being a fictitious 就是一个虚构的电流，就是物理学家他还是不要把它叫做电流，虽然我们电路上我们很习惯的叫一个一个电容的电流可以定义为 I 等于一个什么，但是物理学家的话，他们叫电流的定义，他们怎么说？他们某程度上严格一些，因为他们觉得的话，就是就算我有一个电路，就算我有一个 RC 电，我画在哪里了？不见了吗？这里就算我有一个 RC 电路，这个 I 等于一个什么？什么 sin 什么的，就比如说这个 I 等于一个I0 sin of omega t 加 phi 这样一个东西，我们就通过它，但是实际上的话，没有任何的电子，no electron 没有电子，实际上是通过这里的没有电子通过去，它只是看起来有个电流在通过这个电容，只是说这些电子其实是电子是冲到这里移开这里或者是电流冲到这里，有正电荷累积在这里，有负电荷在累积，然后当你的 AC 反过来的时候这些电荷就是会放电，然后冲到另外一边，然后来回，没有实际的电子通过这个区域，所以物理学家他不愿意把这个电流叫做电流，他还是你就算要叫电流，我把它叫做一个 fictitious， 这是一个虚构的一个虚构的电流那这个虚构的电流，他们叫虚构的电流也不好听嘛，所以叫做位移电流叫做 displacement current ID， OK， 因为它的意思是说 在这个式子在这个式子里面，这个空间比较多。好，因为这里是一样的嘛，那这里的话是 μ0乘以一个这个是电流嘛，所以这里也有一个 μ0，那这里自然应该也是一个电流，就是怎么说，就是它的等于是 μ0 I enclose 加上 epsilon naught d phi e dt。那这个公式是正确嘛？那这两个能够加起来的话，它们两个肯定是单位相同才能加起来，你不能够把1米跟1秒加起来所以这个是电流的话，这个应该也是电流只是它不是一个实际物理学家愿意叫它叫电流的电流最终把它叫做 displacement current 但是至少的话我们明显看到它们的 SI unit 是一样的。OK， 所以它最终把这个定义成 ID displacement current equals epsilon naught d phi e dt. Okay, and then in that case, if we use ID, then the Ampere-Maxwell's law can be written as this line integral equals to mu0 I enclosed, and then has mu0 ID enclosed. Mu0 ID enclosed. Okay, so this is the static current. This is the displacement current. Displacement current. Okay, encircled by the integration loop. Okay, so this is the displacement current, and and here it also tells you that the B field, if we consider this ID to be a known value, we can actually derive the B field in the capacitor to be like this, and then the B field outside the capacitor to be like this. Okay, do you think these two formulas are familiar? you have seen this before? Yeah, the answer is when you consider the static current. Okay, the B field will be like mu0 I over 2 pi r if it is outside. Okay, and then if it is inside the wire, it will be like this. Okay, so we can check out the chapter 29. Okay, chapter 29, we should have derived this before. Which is here. Okay, so at that time when we try to consider here we have a wire with a radius. Okay, so when we consider the B field inside the wire or outside the wire, then the B field will be like that. Okay, so this one is simply like the Ampere's law. Okay, Ampere's law, and then this one is a little bit different because the radius is larger, but the area we only consider the inside part, so that this one is like a linear increasing with respect to the radius. So here it is actually the same case. This is actually the same case. So you can completely repeat the derivation for these two equations just by changing the I into ID. Okay, so nothing special. I don't try to write it again. But here we don't have a wire. So actually what we consider here is here we have a capacitor. So here we try to draw a Ampere loop. Okay, as you know, the Ampere loop is not a physical loop. It can be an imaginary loop. So here, if we consider an Ampere loop which is smaller than the radius of the capacitor, okay, so this is inside, so the B field is this one. Okay, if it is if this loop is larger or equal to the radius to the capacitor of the capacitor, then it is outside, so it follows this equation. Okay, so I think this is nothing special because you have already looked at this version for the static current. Okay, so here we have another sample problem. So here it says the circular parallel plate capacitor is being charged with a current I between the plates, what is the magnitude of this line integral in terms of mu 0 I at a radius r equals capital R over 5. Okay, so here we just make use of integration of a b dot ds, and then here the displacement current. Actually, this I is the displacement current, so will be mu 0 I d enclosed. Okay, so this is the Maxwell's law. This is the Maxwell's law. So here R equals capital R over 5, which means R is smaller than capital R. So in that case, we assume that ID enclosed, we also assume that I is uniform. The current density is uniform for this capacitor. Yeah, I mean the displacement current. Yeah, because the E field is uniform, we will assume that. So the displacement current will also be uniform. So in that case, ID enclosed over ID will be pi R square over pi capital R square. Okay, so this is the full displacement current. This is the partial within the impedance loop, or I should say enclosed by the impedance loop. Okay, so in that case, this ID is nothing but I here, and so actually we have an ID enclosed is nothing but R square over capital R square times I. Okay, so this is I. So integration of b dot ds is mu 0 ID enclosed, which is a mu 0 R square over capital R square I. Okay, so here we have mu 0 I, and then R square. R we take capital R over 5 here, and then square over capital R square. So this is nothing but mu 0 I over 25. Okay, so for question B, it asks you, in terms of maximum induced B field, what is the magnitude of the magnetic field of the B field induced at R equals R over 5, or capital R over 5 inside the capacitor? Okay, so here we have a B of R, okay, is a function of R, is actually mu 0 ID over 2 pi capital R square times R. So when R is smaller than capital R. Okay, so this one is proportional to proportional to R. So which means the B max is increasing. So B is maximum when small r is equal to capital R. So which means BR over B max is BR over B capital R. BR over capital R, like this. So in that case, B here we take R equals capital R over 5. So B of capital R over 5 over B of R will be 1/5, okay, because B is proportional to R. So the remaining stuff will be 1/5. Okay, or I could write B of R is B max over 5. Okay, so this is the final answer. So what is the magnitude of the B field induced at, so in terms of maximum induced B field, what is the B field? Okay, so BR is B max over 5. Okay, so up till now we have already covered most of the content important in this chapter, I should say. Yeah. So in summary, yeah, this chapter is called Maxwell equation. So finally, we will talk about. So this one is called Maxwell equation, the four fundamental equation of electromagnetism called the Maxwell equation. So all these four laws, okay, we call it the Maxwell equations, and are displayed in this table. So for the first one, Gauss law for electricity, so we learned it in chapter 23. For Gauss law for magnetism, we learned it in this chapter. So the only difference is that, okay, this is E, this is B. And then here we have Q equals over epsilon naught. We have nothing but a zero, yeah, because there is no magnetic monopole, 没有磁单极. Okay, so and the third one is called the Faraday's law. We learned it in chapter 30. And then for the Ampere-Maxwell's law, we partially learned it in chapter 29, and also this part in this chapter. So altogether we call it the Ampere-Maxwell's law. Okay, so of course in the textbook we only learn about the this one is called the integration form 积分形式。那其实它如果更有用的话，是一个叫做微分形式的它会讲这样，它就是这个叫做divergence of E field equals 这样 ，OK。那个是这样divergence of E equals 0, and then curl of E equals negative partial B partial T, and then for this one, great curl of B equals mu 0 J plus epsilon naught partial E partial T. Okay, so these are the differential form differential form 这是一个是积分形式，一个是微分形式一个是微分形式。那微分形式的话，就是手算就没有那么方便，因为算那些 curl divergence 的话很麻烦。但是如果用电脑去算的话，就是可以解一些数值解。因为这些的话，你看到，比如说像这个部分，它是一些偏微分偏微分，所以其实这些是一些偏微分方程组。那 E、B 都有3个方向，可以有6个自由度，甚至8个自由度，应该是，因为 E field 的话，它会是一个 x、y、z 还有时间4个维度的函数。B field 的话也是 x、y、z、t 4个维度的函数，所以总共有8个维度。理论上我们需要有8个方程，但是这里其实你看的话，其实是有不止8个的，它有一些是 dependent 的但是最终还是把那个 Maxwell 还是把4个 law 都放进来因为其实你用3个的话，其实已经够了，就是一个式子的话，已经可以提供你3个维度了，已经可以提供你3个维度，不需要太多的式子3个式子已经够了但是4个式子都放进来的话，那某些问题的话会方便一些。不过这个已经 out of the scope of this course， 就是已经在超出这门课的内容范围所以下面就说these 4 equations explain a diverse range of phenomena. They are the basis for the functioning of such electromagnetic devices as electric motors, television transmitter, receiver, telephone, scanners, radar, microwave 等所以它就是很多现象都是跟这些 Maxwell equation 有关的就包括一些什么电池的装置，比如说是什么马达或者是发电机 它是相反的一个是用电去让这个马达转，一个是转完去产生电。然后就比如说是一些无线的通讯，或者是发射，或者是接收 ，transmitter 就是发射 ，receiver 是接收。有一些电路它会叫做 transceiver 的话，就是它有可以发射，又可以接收。然后比如说电话什么扫描器，我不确定是真的是那个扫描器，还是说那种扫描外太空那种和雷达雷达的话就扫描外太空还有那个什么微波炉，或者是等等很多的现象比如说手机的天线，它也是一个产生一个电磁讯号，或者接收一个电磁讯号的一个过程。OK， 但是就没有讲更多，因为更多的话其实是透过那种 Max Education 的微分形式，可以用电脑去解很多，但是这门课的话就不会涵盖那种内容。OK， 所以到这边为止的话，就是Max Education 讲完，后面的话就是一些比较 hardcore 的物理hardcore 的物理。So the first topic is called the magnets is called the magnets， 就是一个磁铁。So the small topic is called the magnetism of Earth， 就是地球的磁场。那我们知道，小学生都知道的嘛，就是有一个叫做指南针的东西因为这个地球上面有一个磁场Okay, so here it says the Earth is a huge magnet for points near Earth's surface. Okay, its B field can be approximated as the field of a huge bar magnet, a magnet dipole that straddle the center of the planet. Figure shows here is an idealized symmetric depression of the dipole field without the distortion caused by passing charge particle from the sun. OK， 所以这个意思是OK， 我们的地球就是比如说这个绿色的球，它就是假设它是一个地球那它就会产生一个磁场。那有一些带电的粒子进来的话，它就会被改变方向因为你学过一个叫做 Lorentz force，Lorentz force 就是在28章的时候，一开始我们讲 B field 的时候就讲到有 Lorentz force。那如果有一个带电的粒子垂直切到一个 B field 的话，它就会有一个洛伦兹力 Lorentz force 作用到这个电荷身上，它就会拐弯它会加速嘛，它就会加速的话就是改变方向嘛，会改变速度。Okay, so for the second paragraph, it says the direction of the B field at any location of the Earth's surface is commonly specified in terms of two angles. The field declination is the angle left or right between the geographic north 这个是地理的北极还有南极跟磁的南极北极它是不一样的。And the horizontal component of the field, the field inclination is the angle up or down between the horizontal plane and the field direction 什么意思？它就是说这个奥是这个地球的旋转轴，因为这样转的话，我们才有白天黑夜嘛。那它转的那个地方的话是这个转轴那在它偏一点点的，因为旋转轴跟那个地理的北极南极的话也是歪的嘛，因为有人学过那个科学吧。就是那个旋转轴跟那个这个公转的平面是有一个角度的所以它在隔一点的位置的话，它有一个南极北极那磁场的北极的话，其实是靠近地理南极的附近它也不是重叠，所以。然后磁的南极的话，就会接近这个地理北极的附近 它也不重合，所以这个南的话在那个北啊，这个北在那个南，就是你看到这个 north， 那这个是地理的北极在另外一边啊，但是它也不是重合，所以什么意思？所以如果你很靠近这个，所以你很靠近这个磁北极、磁南极的话，你指南针就不能用，因为你指的是磁的南极，不是指地理的南北极，所以越靠就北半球的话，越靠近越北纬度越高的话，你的指南针就越不能用啊，或者是你一个指南针在澳门调好的话，你拿到一个高纬度的地方，它就不准了啊，它就不准了。反之亦然啊，或者是你比如说你达到北极点的话，你用那个指南针可能要另外调的啊，或者是你走一走啊，其实那个方向其实不对的啊。最终的话，你还是要用 GPS 定位比较准的啊。你用指南针的话，在那些区域的话是不会正确的。OK， 所以这个是这个地方啊。那另外一个他在说的是啊，那这里也有说嘛 ，Earth B field represent as a dipole field. The dipole axis mm makes an angle of 11.5 degree with the Earth rotational axis out. Okay, the south pole of the dipole is in the Earth's northern hemisphere 啊，它就是告诉你说哦，它跟旋转轴有一个11.5度的夹角还有的话就是磁南极在北半球还有的那个磁北极在南半球最后有一个叫做 shield the Earth from high energy particles OK， 所以这个磁场对于地球来说重不重要他就告诉你说非常的重要非常的重要有一个叫做 aurora 就是叫做极光极光的话就会在这个磁南极或磁北极的附近就会容易看到，但是它是什么来的？它是一些高能粒子来的，所以你住在那个区域的话，应该很容易比较容易得癌症因为你会容易被那些高能粒子会照射到。那这个跟那个磁场有什么关系啊？那意思是，比如说有一个粒子比如说有一个带电的负电荷这个过来，那来到这边的时候有一个很长的磁场跟它垂直它就会有洛伦兹力Q if you still remember the Lorentz force FB equals Q V cross B okay, so the V is like this and then Q is negative okay, we just ignore it and then V cross B okay, so for this case the B is in this direction, B is in this direction, V is in this direction. Okay, so for the V cross B is pointing out of the page, and then the charge is negative, so it is into the page. Okay, so in that case, the charge will be like this, and then turning into the page, and then go away. So it will not directly shoot to the Earth. Okay, like this. Okay, even if you are slightly higher or lower, okay, norther or souther, then it is still okay. But the idea is if the high energy particle is shooting from this direction, okay, almost from the north pole of the B field, okay, it will be like the B field is pointing to this direction and the V is pointing to this direction. So V and B are also have a 0 or 180 degree, depends on whether you are from the bottom to top or in this direction. So in that case, V cross B will be nearly 0. So in that sense, the force acting on this high energy particle will be very weak. So the particle will directly shoot to the Earth, okay, and pass through the atmosphere. 就是它会经过那个大气层，会电离那些大气那电离那些大气的话，其实就是它打到那个大气的那些分子嘛，所以电离你就会看到极光 那你看不到的可能就会打下来啊，就是会被照到啊，就会被那些高能粒子打到，那你就会变得比较高能嘛。OK， 所以这个磁场的话是蛮重要的。我如果没记错的话，是海王星也有一个磁场的，海王星也是有的。那其他的星球的话就比较没有。但你如果看过一些科普的新闻的话，其实地球的磁场也是在来回震荡。其实它经过一段时间，它可能西南极又变成西北极，西北极又变成西南极，所以其实也一直在变的，也一直在变的。但这个时长我也不确定了。Okay, so for the next part, we go into the hardcore physics stuff called the magnetism and electrons. So 这个的话就是探究这个磁场是怎么来的是怎么来的。Okay, so for the first case is called the spin magnetic dipole moment. Okay, sorry, spin magnetic 自旋的磁偶矩自旋的话，那高中化学就应该学过嘛，就是什么量子组态，什么 n 什么我也忘记了，什么 μs 什么ms 什么之类的这些。那如果你还记得的话，他就会告诉你说，电子有一个自旋叫做正负1/2要不然顺时钟，要不然逆时钟。这个是怎么来的？那些什么量子数是怎么来的？它其实是需要解这个 Schrödinger's equation。我今天也没有穿这个 Schrödinger's equation 的衣服来。Schrödinger's equation。Schrödinger's equation 长什么样的呢？IH8 partial t，OK， 这个 phi 是一个波函数嘛，那这个是一个 Hamiltonian， 是一个能量等于一个负的 h8 除以2m， 然后Laplacian of phi，OK， 所以这个是 kinetic energy， 那它就是 kinetic energy 加上一个v phi， 这个是位能，所以它就是总能量等于动能加位能，总能量，所以这个是 Schrödinger's equation， 然后解一个原子模型，然后再加入相对论的效应，才能够解到这个，所以我还不知道怎么解。我大学的时候有修过近代物理在这大三去修的，当时教的是 Schrödinger's equation， 没有考虑相对论效应。它只能够解出前面3个那些什么轨态的那些氢原子模型的那个位能，加一个氢原子轨态的位能进去，你就可以解出一些，但是那些数学已经难到看不懂的，正常人应该是看不懂的，我还是在正常人的范围里面，所以我也看不懂，所以很难的反正就是很难那这个的话就更难的话，就还要考虑相对论效应，我就不知道怎么考虑了。我只是要知道要考虑而已。对，所以你不要问为什么。所以我为什么一开始就说这个是一些 hardcore 的 physics，因为这个是跟最困难的东西，物理学普通人听过的2个东西，最困难的2个东西有关，一个是量子力学，一个是相对论那相对论的话是1905年的狭义相对论，跟1915年的广义相对论还有15年到25年比较提出来就是量子力学的那个10年的话，就是1915年到1925年就是量子力学开始发展的年代。OK， 所以简单来说的话 ，OK， 所以简单来说的话，就是电子的自旋它就会产生磁场而 有这个磁场的话，它就是一个 magnetic dipole， 它就会有一个 magnetic dipole moment， 就是这个 μs， 它就会这个是 S8， 然后 E 除以 m 啊 ，E 除以 m，E 是常数嘛 ，E 就是 1.6乘以10的负19次方库朗，然后这个 mass 就是电子的质量，就是9.11乘10的负31次方。那这个 S 是什么呢？这个 S 啊就很奇怪的，它就会量子化，它就会量子化。我听的时候我也不知道干什么的，反正它的意思是告诉你，这个 S 在 Z 的方向我们可以测量，我们可以测量 a measurement along a Z axis 因为这个是一个自旋，那可以它按照任意方向的自旋，但是你不能够测任意方向的自旋，你只能够测 Z 方向的自旋。当你测 Z 方向的自旋的时候，它就会量子化，它就会跑出来这个 ms。正1/2或者负1/2啊，那这个 h 除以2派，通常这个量子力学的话，他们会h 是这个 Planck constant 啊 ，Planck constant 普朗克常数啊，高中物理可能会学过。那他们量子力学的话，他们会常常会定义 h bar 等于这个 h 除以2派，因为 h 除以2派是常常一起出现的，所以他们就用一个 h bar 去代替，所以这里也是一个 h bar， 这里也是一个 h bar，OK， 所以这个 h 是6.63乘以10的负34次方，所以这个就是要解这个 Schrödinger equation 才会跑出来这些量子化，当然也要考虑那个相对论效应啊。那如果不考虑相对论效应，它还是会有一些会有量子化，其他的轨度那些什么量子数。那会跑出量子化的原因，数学的原因是它是一个偏微分方程，它是一个 boundary value problem。boundary value problem boundary value problem。之前我们学这个常微分方程的时候，我们是 initial value problem 或者是 initial condition problem， 就是一个起始的条件，这个是一个边际条件，边界的条件。当这个边界条件固定了之后，它就会只有一些模态它会留存下来。就好像如果你会乐器，就比如说你会弹钢琴或者是拉小提琴的话，那个弦两头是固定的，它就是一个 boundary condition for the string， 就是那根弦的一个 boundary condition， 这一个边界条件，它固定，它不能够两头向下动，它只能够中间动。那所以的话，它只有一些固定的频率，就是这个会是波长的一个整数倍，才能够在这个弦上面共振出来。其他不是整数倍的，它就没有办法长久的维持下来，所以它就会有这些所谓的量子化，因为你的波长要跟这个 boundary condition match。但这个是一个古典的一个物理的一个你们比较容易理解的一个状况。这个的话就是量子力学，你眼睛看不到摸不到讲这些就已经很玄学的状态，已经很玄学的状态，所以大概是这样。所以的话就是这个是 Z 方向的你带进去就会有这个 μs， 就是这个自旋所产生的这个magnetic dipole moment。OK， 所以它带进去的话，就是会有一个这个就会用这个式子带进去然后带个1/2的话，就会有这个，它叫这个叫做 Bohr magneton， 它相当于一个最小一个 magnetic dipole moment 的一个单位，它大概是这个意思，OK， 所以就是这样Okay, so maybe we stop here today.